Hello everyone, as introduced, I am Ayush, this is Vivian. Today I'll be taking you through a product development cycle of a high-end electric vehicle. So what I'll be talking about specifically will be the cooling requirement of the vehicle. So I'll talk about a high-end electric vehicle, I'll tell you how we are defining the cooling requirement for the vehicle, what strategy we plan to use to cool it, and how we are cooling it. So I'll be taking you through the entire product development cycle of it. I'll start by telling you a little bit about Ola. Yeah, so I think already you have seen a lot of things about Ola today, but I'll be just showing you the 6 cases in which I've divided the work that Ola is doing. I particularly work in the performance part, but we do have software, we have cell tech, we have design, we recently got the Gigafactory, and we have the Future Factory, which is now ramped up to around 1,000 vehicles per day production. But I'll be specifically talking about performance, in which I work and Vivian does. Coming to our particular case, so I said that I'll be talking about high-end electric vehicles. So how does the product development of a high-end electric vehicle start? So it starts with the market study. Usually the market team does a study of what the vehicles are available in India and how they perform. Based on those requirements of performance, range, and everything, we get a requirement from them that this is what has to be designed. Then we have a specific team to design the vehicle. So let's say they are designing the vehicle, they spec the motor, they spec the battery, they spec the tire, everything. So every gear ratio is designed and the vehicle model is fixed. Once this model is fixed, it comes to us to design the cooling requirement for it. So what we have to do is we have to look at the heat loads of the entire vehicle and then decide what will be the cooling requirement. How much kilowatt of heat has to be taken out from the vehicle so that the vehicle can operate without degradation. You can see I have highlighted the word degradation. So that is what I'll be focusing on, that I'll be making sure that the vehicle does not degrade prematurely. So how do we calculate the heat loads in GT Suite? Okay. Can someone check please? Yeah. So I'll be talking about 2-3 things, the motor, the battery. I'll be focusing on the battery today, but we can calculate the heat loads of all the components in GT Suite. For the battery, it is pretty straightforward. We know the resistance of the cells and we know the current that will be required for any drive cycle when the vehicle is being driven. And similarly for the motor, we have the efficiency, so we can get the heat load. But currently I'm focusing on the battery, so I'll be talking about the battery today. So I will be showing you 2 things today. This is battery 1 and this is battery 2. I am not allowed to tell you what exact configurations they are, but I will tell you that battery 1 is bigger and battery 2 is smaller. Then I'll be using a highway drive cycle, which is an aggressive cycle, which we are just using here to showcase you how we define things and how it's just an example. So this is a highway cycle. Just for some reference, I'll tell you that the speed is around 120 on average in this cycle and max touches to 190. So let's say we are using this drive cycle and we are trying to predict what the heat load for the battery will be. So if you see the yellow graph, that is the heat load that GT calculates inside the model. It is calculated based on the current and the resistance as I told you. But let's say you are taking this heat load and you are talking to the designers that the kilowatt which you need to reject to the environment to make sure that the vehicle does not degrade, then the value will be very high. So if I tell you just for reference, the value on average for the yellow graph is around 1. But if you look at the maximum value in both graphs, one graph will give you around 12 kilowatts, which is very high. And if you tell that to a designer, he will be shocked and he won't be able to design the system. So just for a simpler way to talk with the designer, what we have done is we are taking the moving average. So if you look at the red graph, that is a better representation of how the heat load will be in the vehicle. So let's say we know the heat load now, and I have come up with the heat load, but still I can't give that value to the designer because that entire heat load is the entire heat load of the battery pack. If he rejects that particular average heat load, the battery will just not rise in temperature, which is overkill. So we don't want to do that. So what we do next is we develop a thermal model for the battery pack. So you can see the thermal model for a battery pack. What I've done here is I've taken a section of a battery pack. So this is not the entire battery pack. I've just taken a section of the battery pack. And we are changing, as we are in the product development stage, so we'll be changing the configuration of the battery pack, the SMP configuration. So I take the section because I don't have to model it again and again. I can use this model to model any SMP configuration. So I've taken the vehicle model, I've developed a battery model, I've integrated both just to see how the temperature rise will be in the battery pack. So if I show you these graphs, if you focus on the green graph, that green graph shows you the battery temperature when there is no cooling in the system. So green will be the temperature rise in the battery pack if you drive in highway cycle in this particular vehicle for battery 1 and battery 2. So now what I want to do is, previously I told you that the moving average, the red graph, which I've shown here as well, will be the cooling requirement. But it cannot be because I told you then the battery temperature will not rise at all. So what we have done is we are just doing a dummy calculation, just basic mathematics, that we are trying to say that let's just reject 500 watts of heat continuously. Or let's just reject 1 kilowatt of heat continuously. So what will happen to the battery pack? Let's say I just take out continuously 500 watts from the battery pack. What is going to happen? Will the temperature rise? Will it not rise? What will happen? So if you see the yellow line, that yellow line is the degradation temperature in the battery pack. Currently for us it is around 55 degrees Celsius. So I want to keep the temperature of the entire cycle below 55. This is currently my product requirement. I'm not telling you the exact one, but let's say this is the product requirement that I don't want the temperature to cross 55 throughout the cycle. So if you see the ascending graphs, the green graph is reducing. So in the case of battery 1, you'll see that the blue graph is where we are below the degradation temperature, and it is around 1 kilowatts. And for the battery 2, it is the blue one, which is 2 kilowatts. So this is the value which can be given to the designer, and he can design accordingly. This will be a more accurate description and a more accurate base for the designer to design his cooling system. So this is how we resolve one of the issues. So let's say I've given the cooling requirement that this is the amount of heat that you have to reject, but we still don't know how we'll do it. So at a system level, we also want to propose a strategy which the designer can use to design his system. So I'll be comparing two methodologies here today. One is the coolant plate based one, and one is immersion. I've not named them, but you can very easily point out that the first one is coolant based and the second one is immersion. In the first one, we are just passing a coolant, let's say EGL 50/50 throughout the plate. And in the second one, we are immersing the entire battery pack in a dielectric fluid. These images I have just taken from some paper. I'm not showing you the images of the Ola battery pack, but you can just understand from this how the cooling methodology works. So let's say I'm developing my battery pack model, whatever I showed you previously, specifically for this type of cooling. So I've taken that battery pack, I made some design changes by sitting with the designers, and I have taken a preliminary CAD that this is how the designing will be, this is how the coolant plate will be, this is how the immersion will be. So now, let's say now we have the CADs. I'll not go in the depth of the model, how we have developed it, but let's say the first one which you see is the methodology one, which is the coolant one, and the second one which you see is the immersion one. So I am developing two complete battery pack models which are in detail. They are completely discretized and everything has been calculated, and I'm integrating them with a radiator circuit. So what I'm trying to do, let's say I take the heat out of the cells, I put it through the radiator, I release it to the environment. What will be the impact of the entire cooling system on the temperature of the cells, which we were comparing previously. So let's say I told you that previously it was 1 kilowatt and 2 kilowatt heat rejection. Will this size radiator be able to accomplish the job or not? This is what we want to check here. So we run these models, and this is the kind of analysis which we do. So you might have seen conventionally, what we do is we evaluate a system for a drive cycle. But we at Ola, we don't want to do that. So what we have come up with is a discharge analysis. So what this basically means is, let's say a customer gets a new vehicle, it is at 100% SOC, he is discharging the 100% SOC vehicle to 10% SOC by driving it at a highway, and is immediately plugging it in a hypercharger, and he's charging it back from 10 to 80% SOC, and he's again discharging it from 80% to 10%. So this is an overall cycle which we have just come up with a hypothetical experiment, and we are trying to evaluate the system for this extreme case. So this is the extreme case, and I don't think anything can go beyond this. So we are evaluating both the methodologies, method 1 and method 2. How will the battery temperature be if we are using this cooling methodology or this one? So if you look at the graphs, the red one is the one for methodology 1, which is coolant, and the blue one is for immersion. And similarly, if you come to the battery pack 2, the correlation does not fit anymore, and you see that the immersion is performing worse than the coolant. So why this particular phenomena is observed in these battery packs, I'll be explaining. Because we usually have an understanding that immersion will perform better than the coolant, but it is not always the case. This is what I want to explain here. So also I want to point out here that you can see the speed graphs. So the speed graphs have been modified to make it better for you to understand. Let's say you are looking at the green graph for the speed, you will be able to see that till the battery pack has not derated, that is, the temperature is continuously rising, the speed for both cases, methodology 1 and methodology 2, are the exact same. But as soon as the blue one has derated, you can see that the yellow graph is more visible, because at that particular area of this graph, the methodology 2 battery pack was not able to perform. So the vehicle was not giving the speed which was demanded from it. So basically the vehicle is not performing as we want. So we want to rectify this. So that is how we will select the methodology which is better preferred and better suitable for us to operate the vehicle. Yeah. So why the particular phenomena which I was explaining in the previous slide? So you can see I'm calculating the heat transfer from the cells to whatever, the coolant or the immersion. How much amount of heat has been traveled from the cells to the coolant or the immersion. You can look at the graphs, the green one and the red one. So in battery 1, you will see that the red one, that is from cells to coolant, it was, if you look at the green and red graphs, you'll see that initially the green one is giving a higher value. That is, the immersion fluid is able to take out the heat from cells pretty quickly and better as compared to the coolant. But what happens after some time, because of the yellow and the blue graphs, it is not able to reject to the environment. So the combined effect of both is causing the immersion to perform worse in a longer period of time, because the immersion is a huge volume of fluid. In comparison, let's say I have 2 liters of coolant in that particular battery pack. If I want to replace it with immersion, I'll fill at least 20 liters. So the fluid amount for the immersion is very high, and replenishing it with the same pump which I'm using for the coolant is a very difficult task, and it will not happen. So the amount of heat will remain stuck inside the immersion, which will cause it to perform worse, even though we are expecting that it will perform better. So on a vehicle level, it will vary. And if you see for the battery 2, why this particular phenomena? So the battery 2, the immersion is performing better than battery 1 because the casing of the battery remains same. So the volume of immersion has increased, even though it is not being replenished, but still it is able to take out the heat and store it within itself, but it's still performing better because the volume is very high. Previously it was around 20, let's say in this particular case, battery 2, it will become 30 because I have removed cells, I have more space to fill it with immersion fluid. Yeah, I'll hand it over to Vivian now. He'll explain the control strategy.
Yes. Thank you.
Yeah,
Thank you, Ayush. So, once when the model is ready, we'll be more interested to find the optimum flow speed, flow rate, for which we have worked on a co-simulation model where the control algorithm is in Simulink. So, for the fact that the control algorithm can be easily deployed in the hardware for prototype testing. So that's the reason we have developed the control algorithm in Simulink and have built a co-sim model. So here you can see that there are two lookup tables where we have followed an iterative approach, taking into consideration of the pack temperature, gradient, and also the vehicle speed. So we went iteratively optimizing the lookup table where we are able to comfortably keep the battery inside the duration limits, and also accounting that we don't overcool it. So if you could see, there are comparisons between using an optimized parameters where the Simulink control algorithms gives me, and also having a constant flow rate or blower speed accordingly. So our concern here is to also have a minimal power consumption. So keeping that in mind, we don't want to overcool it as long as it is under the duration limits. So in both the graphs, without the optimized control logic, we could see that we are slightly tend to overcool the system after the second half where we charge and then drive. So this control algorithm helps us to save some energy which can potentially be converted to range. So that's about the control logic for this project. And to summarize, as Ayush has already said, for battery or motor, for any system, we would first calculate the heat loss, which will be based on city driving conditions and obviously using efficiency maps. So once when the heat load is defined, we'll be working on various cooling methodologies, like two things as Ayush has already explained on coolant plate and also immersion cooling. So once when we are narrowed down with the cooling methodologies, then we'll work on control strategies where we come to optimum parameters, which is actually helping us to make the system stay inside the duration limits without spending much energy. And of course, obviously, we get a much return of investment here. We are able to do all these things in simulation before even we start the prototype. So once when we incorporate the optimum arrived parameters into the hardware, so we'll be saving much time on the prototype testing. Thank you.
So just to appreciate what we have done here, so in conclusion, what we have accomplished here is we have reduced the product development cycle by a lot. What we are doing is we are not letting the designers take the time and develop the battery pack designs for the coolings. We are actually telling them which methodology to use, which will work out best in the end based on drive cycles, even at the start of the product development. So we are reducing the time of the design by reducing the waste time of designers to continuously keep on coming up with new designs because this one is not working, that one is not working. So we can have a discussion initially, we can simulate and see what will work, and then they can design around it to save a lot of time. That's all from us. Thank you. Any questions are welcome.